Good morning. All right. This is the moment when we pray to the gods of technology that they will smile on us one more time. It's happening, okay? Thanks so very much to the Center for inviting me to be with you today, and welcome to everyone who's traveled far afield or from local neighborhoods. I'm very honored and glad to be here. The name of my talk is Learning is Moving in New Ways, Designing for Physical Coordination of Mathematical Concepts. But I would like to begin by responding to this question about objects by taking you back a few years, in fact, all the way back to 1970. I think that science museums are awesome. I used to say awesome when I grew up with my South African accent, but in the United States I learned to say awesome. So I want to speak to you a bit about awesomeness, about awe, and about a child who in 1970 went to a science museum. The child was me. I was just 4 years old then. My family was living in Canada for a year, and this is in Toronto, the Ontario Science Centre, or whatever it was called back then. The three of us went there, my two elder brothers and myself. My elder brother, Udi, was 7. My second elder brother, Michael, was 5, and I was 4. And I'm trying to give you here a sense of what it is for a child to go to a museum and what seeds that visit may sow for a lifetime of interest and curiosity. It so happens that we came there to an exhibit which was pretty modest in its appearance. It was a chamber, maybe a glass box, I can't quite remember, that had in it 13 chips. On one side it was black, on the other side it was white. And there was a button. And you pressed the button, and these things sort of flipped and flipped and flipped, and they landed. And then some kind of display told you what are the chances that you got whatever you got. So here there's like 8 white, it's like 1 in 6 or something like that. Well, you can imagine one child after the other were walking ahead and pressing a button, then 1 in 6, 1 in 3, 1 in 10, 1 in 2, yeah, whatever. My brother Michael came up there, and suddenly something in the heavens opened. Maybe you heard the angels sing. He pressed the golden button, and suddenly, this happened. Now, it's difficult to communicate the awesomeness of this, because you might think like, yeah, whatever, like, sure, you got 1 in 8,192. Something about, as a 4-year-old, it was the biggest number I'd ever seen. And something about this, all 13 were white. I was just moved beyond words. And you can imagine whatever, then the next kid probably pushed from behind and came and pressed the button. That was over. So maybe the whole thing was like 1 minute. But somehow that 1 minute began something. It sparked something interesting. This number, 8,000, when I was preparing these slides, I had to actually go back and check, like, so what is actually 2 to the power of 13? You know, 2 times 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 2 is actually that number. And the reason I had to check so many times was that somehow over the years, in my family's collective memory, or maybe it's amnesia, or there was some kind of inflation of the number. Because by the time we were in our teens, we were all speaking about, remember that time that Michael pressed the button and he got like 1 in 100,000? Right, and it was just so amazing, it was so rare. And as the years went by, the likelihood shrank by an order of magnitude about every 10 years, so that by the time we were in our 20s, it was like, oh yes, that time that Michael pressed the button, it was like 1 in a million, like nobody had ever seen that before, and everybody came rushing, and it was just amazing, right? And of course, by that point, nobody's checking the math, nobody's checking the logic, and nobody's thinking, well, yeah, if there's 1,000 kids visiting that exhibit every day, eventually, because by that time we'd forgotten the real number, and nobody really cared. It was about the affect, about the memory, about this collective experience. So that when I was preparing these slides yesterday at the Zurich airport, I thought, maybe my memories, I phoned my father back in Haifa, Israel. And I said, Dad, do you remember the time when Michi pressed that? He said, oh, yes, of course. It was like 1 in a billion, my father told me on the phone. It was amazing. Everything stopped, and the director of the museum came, and all the staff came, and they photographed it, and he was famous. And it's like, what? So later that day, I spoke to my mother, and she said, your dad wasn't even there. He was in the hospital. In fact, that very day, he was operating on a pair of baby twins, Siamese twins, who were just born, conjoined by the liver. And we're like, yeah, whatever, twins, Schmitz, but 1 in a billion, right? So I really had to go and keep checking what that number actually was. About 35 years after that momentous day, that day of the awesome experience, I found myself in a situation when I was still obsessing over this number, and I wanted to try and understand it. So I started looking at where this is the Pascal's triangle, the binomial coefficients, and the bottom row represents the distribution of events for when you have 13 objects in a binomial experiment. So I wanted to understand why exactly we got that. He got, of all the things, right? He got that one. And then I wanted to look, how do we represent this in various ways? And so that one event took me on a journey to understand probability. At that point, I found myself a postdoctoral researcher at the Center for Connected Learning and Computer-Based Modeling at Northwestern University, directed by Professor Uri Wilensky. And so I had these cool tools that I could use, and I was programming with them. So I built in NetLogo a model. Here it's not 2 to the 13th. There are only 9 different events. Each one of those 9 things can be either green or blue. And I wanted to actually see all the different permutations. 2 to the 9th, there are 512 unique patterns of green and blue. I actually created them. I wanted also children to see these things. I wanted to see, why is it that we get this distribution? And it's ineluctable. I wonder what the translators will do with that word. Ineluctable. You get this, no matter what you do, you get this shape. I was obsessed with this. I decided to start taking this to schools. So I started my research working with children, first in the lab, and then later going into classrooms, 5th grade, 6th grade classrooms, having whole weeks or even 2 weeks of units on this. And in fact, let me show you something cool. It just so happens I have this object here. The last time I showed this in a talk was 12 years ago. And maybe I'll ask Ilona to give me a hand and to unfurl this. Let's keep walking backwards towards there. Here we have a poster that it took 2 6th grade classrooms a whole week to prepare. This is, if you can go lower, then I can, thank you. This is all 512. All right, we'll put it sideways, but it usually stands tall, which was really awesome. This is all 512 possible permutations on that 3x3 thingy, okay? That all the children built, and each child came later and said, this is the one I built, and here's mine, and you see this is it? 2 classrooms over 3 lessons plus working at home built this thing. And sometimes people ask me, tell me, is mathematics about the world? I mean, this is so abstract, this is not. No, the children actually thought of this as real things, and they said, you know, when you run that simulation, you get more of the middle columns because there are more of them. Because they spent the whole week building those things, they really knew that there were more. Thank you very much, Ilona, for the kind help. By then, I'd moved to Berkeley, and I found myself to be an assistant professor. And of course, when you're an assistant professor, you need to publish or perish. So I figured out I should write up all of these studies we'd been doing. So then came all these papers, speaking about the research we did, about my own obsession with this probability thing. And fortunately, all of this actually led to me getting tenure. So if there are any children here, please remember smoking it can kill. So my question is, how do we assess all of this? I mean, if back in 1970 you wanted to know the impact of that exhibit on me, of the flipping black and white chips, what exactly would you have measured, right? Could you wait 50 years? Would you have a grant for that? I mean, we're talking about a life-changing event, a random event, if you will, that lasted no more than 1 minute, but then, in a sense, lasted a whole lifetime. So now, as I watch my own children going to museums and having these kinds of experience, I kind of wonder, where will all of this go? Where in 35 years or 40 years' time, what will be this child's thought or contribution or ideas that began from that? And how would we have assessed that? So if it can take 40 years for an experience at a science museum to have an impact, then this implies it might be meaningless to evaluate museum exhibits with just like a single post-test. So please don't evaluate exhibits by assessing learning with a post-test. Because you know what will happen then, right? We'll want to get good assessments. And so, of course, we'll start teaching kids what they need to know in order to achieve high scores on their assessments as though it's the kids themselves we are testing. Does that sound familiar? That sounds a bit like school. So I'm asking Copernicus, please don't teach in that sense at museum. Or in the sense, please don't schoolify museums. I think we should do something better. I think we should museumify schools. So let's find a way of bringing to schools this kind of the awe. And awe, I kind of looked it up. How would you say it in Polish? It's maybe podziwy or oszołomienie. Did I say that? Oszołomienie. Well, so I mean, I don't mean awful. That's strasznie. I mean awesome, niesamowite. So, it's all about the sense of awe, okay? And if you think to yourself that actually, why is it that a 4-year-old finds it so thrilling to see all 13 chips on the wire? I mean, it's not about the math, is it? It's not like I knew the math. I never seen even such a big number. But something about all those 13 chips in the same color seemed familiar or seemed exciting or seemed unusual. Well, it turns out that kids are really smart. In fact, children as young as 6 months old, they know, I mean, lots of studies have been done on this. They know that if you take 4 marbles out of a tub of equal numbers of mixed marbles, they know it's really unusual to get all 4 of the same kind. They can't yet talk to us, but there are other measures. Kids as early as 6 months old. And yet often we want to rush these young children too fast towards stuff like that, which is not quite appealing. So the question is, how can we bridge these two kinds of things, these awesome tools and the mathematics that we want to get to? This is an old question in education, constructivism, sociocultural theory. To the extent that we want to foster big ideas from interventions with objects, with hands-on tools, etc. How do we make these things tie? How do we make these things go together? Because when children look at an object like this, they don't yet have any connection. They kind of say, what is this? What does this mean? I can't make sense of this, or this makes no sense to me. I mean, do you believe this? Like, what grounds do you have to believe this? And if so, why? Right? Why do you believe this? And what in the world is this? Or actually, what in the world is this? So where do we begin? So here's some wisdom. Like, what is the use of all these symbols, right? Why not begin by showing children the real thing so that they may at least know what you're talking about? So as a general rule, never substitute the symbol for the thing signified unless it's impossible to show the thing itself. Because the children's attention is so taken up with the symbol that they will forget what it signifies. I wish I could tell you I wrote that, but I didn't. Any guesses? I can give you clues. It's not Jerome Bruner, it's not Jean Piaget, it's not Montessori, it's not even John Dewey or Lech Walesa. This goes back many, many years. In fact, it goes to 1762. It's kind of cool. I mean, or ironic. I'm not sure if I'm happy or... I mean that for 250 years we've already known this, but like Oscar Wilde said about the weather, everybody talks about the weather, but very little is done about it. This was written by Jean-Jacques Rousseau in his book Émile. I very much recommend book number 3. So the big pompous question to all of us is, how do you engage children in interesting activities that will give rise to meaningful learning of big ideas they should understand and use if they are to flourish in a wonderful, complicated world and make it a better place for themselves as well as for us? Well, a scholar I really admire, Pat Thompson, says the most usable meanings are those that are richly connected with imagery action and that tie into other meanings. So what does he mean by this imagery action? Let's go back to Rousseau. He's talking about showing children the real thing so that they may at least know what you're talking about. Right? There's this real thing and there are the symbols. Okay? And we're looking somehow to connect these things, as I mentioned before. The real things and the symbols. So these are the kind of questions that I deal with as a researcher. My background is in cognitive psychology, PhD in the learning sciences. My approach is design-based approach, and the framework I've been developing for the past 25 years, I guess, is called Embodied Design. It's a framework for creating artifacts and activities and facilitation so that children can connect between their naive way of seeing the world and the normative scientific cultural way of seeing this very same phenomena. So that we can answer questions about activities and environments and all these questions that designers ask themselves when they create these artifacts. And yeah, so embodied design, it deals with 2 kinds of activity genres. One of them is, so it's fostering mathematical insight via perception-based and action-based experiences. What I just mentioned now really and briefly about the probability and just children as young as half a year old already being able to see or to intuit intuitions, I call that roughly perception-based. And I won't be speaking more about this now, but I'll be getting back to that later in my methods session. Because I want to speak to you today about a different genre, the action-based experiences, which finally brings me to the beginning of my talk. So learning is moving in new ways. And I mean that in 2 meanings, in 2 senses. One is that in order to learn, children need to move, physically move in new ways that they've never moved before, and only then to start signifying and sort of mathematizing those movements as their means of accessing new concepts. But I also mean that the very idea of learning, the theoretical construct of learning that people study, it in and of itself is moving in new ways within the theory. So I'll be speaking about designing for physical coordination of mathematical concepts. So I lead a lab called the Embodied Design Research Laboratory, University of California, Berkeley. And the work we do, as I say, it's called design-based research. It's kind of an interesting approach. It's an approach to educational research where we're all passionate educational designers, but we're also researchers. And we always begin from some kind of problem of practice. Children are not understanding algebra, fractions, probabilities, something like that. We come from design, but then the practice of design, it constitutes a context from which questions emerge that are relevant to the learning sciences. And these questions emerge during ideation, engineering, design, and most of all, I find, during data analysis, where we see kids doing stuff and we don't understand what is it that they're doing. And we look at it over and over, and we read the literature, and we speak to colleagues, and we try everything, and we don't understand. We are seeing new things. So in a sense, by seeing new things, we are honing, we are sharpening our own design problem, because we learn better what it means, what the challenges are for children to connect between the naive and the scientific views on phenomena. I've used the Escher picture here because design-based research operates in cycles where we are driven by a theory to try and solve some kind of design problem. We engineer and we build artifacts and take it to children. And then once we've taken to children, we can actually implement and observe and collect data, then analyze the data, and then based on that come back to a theory. The idea comes from Alan Collins, in the late 80s, was looking for some kind of model for educational scientists to make, well, to education researchers to make education research into more scientific, to go beyond school psychology. And he took his model from aeronautics, and he said, aeronautics, the best kind of airplane you can build, that aeronautics engineers can inform the building of, is really a materialization of the best possible theory that they have. They use the best theory, available materials, they build the airplane, they try it out, maybe it doesn't fly as well as they thought, maybe they thought wings should be this way. It didn't fly as well, so that means that the theory was incomplete. But it's through the implementation that they learn something new, which is why also designers like me, I like to show things that didn't work, because that's how we learn. As Ilona said, we are like the students in a sense. We're all curious, we're all learning together. And these are cycles. And many of us at times will use technology, but we need not. I've used things as simple as paper, or as you saw, marbles, but other times I use artificial intelligence, machine learning, parallel processing, modeling and simulations of multi-agent computation models, and all depending on what I need. But I'm not like a techno-centric person. I'll use anything that's important. So ultimately, we're trying to build tools so children will be engaged, children will learn, and, well, yeah. I have a colleague called Manu Kapoor who speaks about productive failure, so I like to think of that as showing. So the work I do, I like to think of it as in a tradition of these giants, names that you may have come across. 1837 is an interesting year. 1837, I wonder if anybody knows what. That year is something momentous happened then. It was the very first day of kindergarten. Before that, there was no, like, kindergarten. There was no, like, kids were little adults who could already start working and learn the trade. And Friedrich Froebel, in his book called The Education of Man, probably today it would have been The Education of People or Persons, he thought that children are different. And he is the first person who created a systematic scheduling and a regime with multiple manipulative objects that he called gifts. And in fact, this one down here, these are spherical balls of yarn connected to string. That was gift number one. All right? So after him, of course, came many famous names like Montessori and so on, Freudenthal, Gattegno, and Dien. And I even brought here a photograph of Seymour Papert's turtle. It was this large thing that children would program and then sit on while it would take them around places. Now, turtles are mostly virtual objects on the screen. So as I said, I think of my framework as embodied design, and the idea that we are constructing the means, the tools, the things for the children to construct the meanings. Okay? We as designers construct the means for the children to construct the meanings. And the idea is that children will experience first and analyze later. We want them to build mathematical concepts from perception, action, aesthetics, and common sense. And then always the question is, what should they experience? What should they begin from? So I have a couple of slides now on the general kind of philosophy or theory of knowledge and learning that guides our work. For a very long time, and probably the middle 20th century was the apex of that, people thought of the human psyche as essentially like if you were building a robot with sensors and actuators and a computer in the middle. That was like the reigning metaphor. Thought, well, you have a sense of touch, of taste, of smell, of sight, and of hearing, and these information goes into the brain, and then it is processed amodally with no modalities, just kind of symbol processing, and then something is sent back out to the body, which responds. Well, that paradigm is sort of moving out, and we're seeing a rise of alternative paradigms, loosely called embodiment, sometimes called enactivism, or speak about the embeddedness of the mind, or the extended mind, or the distributed, etc., where we think that actually there is no amodal, so non-modal. There is no such thing as a non-modal reasoning. When Larry Barsalou visited our department a few years ago, he said it used to be these embodiment folks had to prove themselves, but now it's the other way around, because they've used fMRI and we haven't found symbols in the head. We're still looking for the symbols. We haven't found them anywhere. Instead, we see that when people are reading and thinking and reasoning, areas fire up in the brain that are related to the body parts that would be participant to those actions, even as we're reading. And Damasio speaks about somatic decisions through the body. So there's like this shift in paradigm we're seeing these days into, as I said, embodiment. So much so that testimonies from famous mathematicians and scientists are supporting us. This is Terence Tao, possibly the most famous living mathematician right now, who it's painful for me to say, at the age of 24, he was full professor. I'm 51, I'm only submitting my papers now for that. He's at UCLA, and he says when he reasoned about mathematical ideas, he says, I've used the metaphor, I'm quoting, used the metaphor of an egg yolk flying in a pool of oil, or a jet ski riding ocean waves, to understand the behavior of fine-scaled or high-frequency component of a wave when under the influence of a lower frequency field, and how it exchanges mass, energy, or momentum with its environment. In one extreme case, I ended up rolling around on the floor with my eyes closed in order to understand the effect of gauge transformation that was based on this type of interaction between different frequencies. Okay? Because sometimes I hear colleagues or people say, well, embodiment, yeah, well, it's good, kids can count and maybe add, subtract, but the moment you go like fractions, or whoa, algebra, whoa, calculus, forget about it. It's abstract, right? So listen to this skater dude in UCLA. It is believed by people espousing ideas from enactivism that the whole idea of abstractness is something that needs to be queried and revisited. That the word abstract doesn't really speak to our phenomenology, doesn't speak about the mind. It's this word that is used when you don't yet understand something. But understanding is the process of concretizing, making things concrete for yourself. And later on, I'll show you something which is radically simple, and I'll say that, well, you could say it's abstract, but it's really concrete. So here's a slide about enactivism. So this is work by Francesco Varela, Evan Thompson, and Eleanor Roche, a book from 1991, cognitive scientists, philosophers, who were trying to take a different take from embodiment perspective, enactivism. And they say, in a nutshell, the enactive approach consists of 2 points. Perception consists in perceptually guided action. That means, well, yeah, anatomically and physiologically and functionally, you could say that my eyes are separate from my hands, and that's how you would build a robot. But in terms of evolution, and in terms of our phenomenology and the underlying sensory motor schemes, perception and action are irreducible, which is always a strange idea for people hearing for the first time. But in terms of evolution, we first had the ability to move, and later perception evolved as a means of guiding our motion. So wherever you speak about perception, you should always ask, perception for what? It is always perception for action. And once again, we can measure them separately, but when we theorize, conceptualize, and analyze, we should think of them as one for the other, perception for action. And here's the second sentence, which is a bit tough to parse, but it's a key sentence for my work. Cognitive structures such as the thing that eventually lead to, concepts, such a concept as proportionality, they emerge from the recurrent sensory motor patterns that enable action to be perceptually guided. So what they mean by that, there are certain actions we learn to do, and we learn to do them because we've trained our perception to guide our actions. So if we do those actions more and more, then we build these sensory motor patterns. And it is from these sensory motor patterns that cognitive structures emerge. So this is as far as I'll go with theory today. But the reason I show you this is because as design-based researchers, we are informed by philosophy and theory of learning in order to design. In fact, I use this sentence as my template for embodied design. Because I ask myself, well, what are the cognitive structures that I want children to learn? For example, proportionality. So then I dig deeper and say, well, if that's the concept, what sensory motor patterns might it come from? What might be a sensory motor pattern of proportionality? But to answer that, I need to dig yet further into this nested structure and ask, well, what are the actions that I want students to be doing, and how would they be perceptually guided? Okay? So this one sentence, it's a very dense, packed sentence, and it took me like 2 years to understand this one sentence. But that's enough for me for a lifetime of work, guiding the framework of embodied design and work within that framework. So now we're going to turn to an example. And once again, I'm speaking to you today about embodied design, which is the framework. I said there are two activity genres. One is the perception-based, which, like the probability stuff, was an example of that. And the other is the action-based, which is what we're speaking about now. I gave you some theoretical background and explained how I use that theory to inform my design thinking. And now we're going into a, I guess you could call it a case study. So anyone who's taught children about ratio and proportion or multiplicative structures has probably come across this kind of idea that, well, you pour say two blue cups and 3 yellow cups into a tub, and you get this color. And now next time you want more green, and it turns out you need, double. And then the question is, how many yellow cups do we need? Now, anyone here who's taught children elementary school into middle school and beyond, you may expect what kids will say. Does anybody know what kids say in this case? 5, yeah. The reason they say 5 is they say, there's 2 ways you can think of it. Either, well, we have 2 more, so we need 2 more here. Or they can say, well, we have 1 more in the yellows, so we need 1 more over here in the yellows, okay? Now, what does it mean that we know that it's 6? Like, where did that come from? I'm always curious when as adults, we think about some simple concept, and also we say, oh, that's so obvious. Like, why is it obvious? Is that something deep, or is it just that we learned how to solve it? I'm not always sure. For children, this is not a simple idea at all, because for them, equivalence has always mean you have the same amount of stuff on both sides. So where is the sameness? They're seeing instead that the difference here is 1 and the difference here is 2. So how can different differences be the same? Okay? And for us, the question becomes, what might be an embodied design for proportional equivalence? And at this point, I really want to emphasize that teachers know this stuff. I'm not teaching teachers anything new that they don't know, but they don't necessarily have the resources in their classrooms. We need to, as I say, museumify school. They don't necessarily have a way of showing, to create conditions where children can challenge that, or even better, when children can discover on their own, where children can try to put 5 cups and see it's not quite right. Because with these cups, it's difficult because it's a mess, and you can't quite tell the difference. If you've put only 5, it will be difficult to measure. You cannot take the colors out, and anyway, it's difficult to assign numbers. So even though teachers use this, they call it the recipe model, this and that, and then more stuff, this and that, it's really difficult to create conditions in the classroom where children will have a discovery-based experience where they can experience what we call a cognitive dissonance. So this is our first try. And you see Mark is cranking this thing and Becky is holding on. And you'll notice that there are two pulleys here. The pulleys are of different diameter. In fact, their ratios are 2:3. So when Becky's holding onto these handles, hands are going up and down at different rates, which correspond to 2 to 3. So this was our very first try to concretize, to phenomenalize, to put into a thing, into an object, as Ilona said earlier, to create an object that will be interesting. But as I said earlier, as designers, we love showing things that didn't work, okay? Just imagine if, I don't know, the CEO of Apple came and said, let me show you something that doesn't work. You can just think what will happen to the stock of, right? So the reason this doesn't work is, and maybe it's obvious to some people, but Becky could just fall asleep there. I mean, she's just like holding on, and she doesn't have any particular task, so she's not attending to anything in particular, and so she's not surprised by anything, so she's not challenged, and she doesn't need to reconfigure her thinking. It's just something that's happening there. So we call this mathematics imagery trainer number 1 and moved on. Whenever you see number 1, it means later came number 2, right? Like with world wars, right? So it was about then Johnny Chung Lee hacked Wiimote, and so he could put the sensor there and move objects on the screen with his fingers, so he said, we'll do that too. So mathematics imagery trainer number 2, and it's lots of arrows here, it looks very sophisticated. It's basically like a video game, okay? And in this video game, the kid is holding 2 remotes, okay? And with these remotes, she's controlling these objects. So this is what happens, all right? Children walk into a room. They volunteered, or their parents volunteered them to take part in some experiment. They don't even know it's math. And we put them in front of a desk. So just imagine that the desk is here, because I don't have it, but I need to have that kind of base here. They're sitting in front of a desk, and there's this large screen in front of them, and we show them, here's one remote, look, it moves that cursor on the left. Here's another remote, it moves that cursor, and when they come in, the screen is red, all right? And we say to them, make the screen green. So they try moving one, and it's red. They move the other, and it's red. They try moving both, and real fast, and it's red, and they try flailing there. Suddenly, the screen is green. Now, why is it green? It's completely arbitrary. I mean, we are the guys who decided this little weird animal behaves this way. I mean, it's like the kids are encountering a new animal they've never seen before and trying to learn what are its behaviors. We've set it up so that the computer processes the height of one cursor and the height of the other, okay? Like the height of the cursor over the base and the other, and then it looks to the relation between them. So here it's 1/2. I'll speak 1/2. Those are examples. It's just easier to speak about those. But later we go into more complex ones. If the ratio corresponds to what the experimenter has set up on the side, the screen will be green. Otherwise, it will be red. That's how this machine works. Now, the kid finds the green and says, okay, now what? You say, well, move your hands, keeping it green. What would you do if you were that kid? And by the way, adults do the same. Can you show me with your hands what you would do? If you, yeah, you're all doing that, right? You just do that. And that's what adults, it's not like adults come and say, oh yeah, this is going to be a quadratic equation, or this is going to be, I know. That's what we do. Because there's this big screen, and there's no frame of reference, and remember, the software thinks of this as a height, but for the kid, it's just a thing here in space, another thing in space. These two things, and they know that there's going to be some kind of logic here, but they don't know what, okay? And so they say, well, let's try something. So let's try, and they move their hands, and it goes red. And then they fix it, okay? And then they fix it, and now it's green again. So then they go up more, and it's red, and they fix it again. And with time, they start noticing that their fixes are always that way. And they say these kind of illogical things. It's like, they say, it's kind of like I was trying before, where you keep the same distance, only that the distance needs to grow. So you see how they already trying to anticipate the fix by putting the fix into something that they know to do. And first they say, oh, it grows. As it goes up, it grows. But then they say, oh, I need to make it bigger. So you literally see what Piaget called the assimilation and accommodation. You literally see it in front of your eyes as they figure out that it needs to move in that way. Okay? It is at that point that we bring onto the screen a grid. Now, this is the magical moment where the naive connects to the culture. Okay, remember I told you that we're trying to bring these two things together. And it's always a fascinating moment, because what happens when you bring this grid up? Children have been moving in a continuous space, moving their hands simultaneously. And now comes along this grid, and they raise one hand, and sooner or later, one of the hands reaches a line, and they just park their hand there. And they keep moving the other one, and then, oh, it's green, so they move this one. Before I know it, they're saying, oh, for every one I lift up here, I lift up two. 1 and 2, 1 and 2. The point is, we didn't tell them to do that. We had a task, and we brought a resource. They identified within this symbolic artifact embedded utilities for doing better what they've been trying to do. They recognize these lines as enhancing either the enactment, kind of doing better, or the explanation, telling people how to do it, or how they think, or the evaluation, thinking about their own work. And so they adopt it. But in the course of adopting it, they shift into a different way of seeing and thinking. It's no longer simultaneous, it's sequential. No longer within a continuous space, it's a discrete space. And no longer qualitative language. The higher I go, the bigger, but quantitative language. For every 1, it's 2. So I think of this as again, as modest as it might look, just put in a grid, I think of this as the naive scientific interface. This is a place where children see these resources, use them, but in the course of using them, shift the way they think. And then we bring in numbers, and we see different kinds of behaviors. Eventually, we bring in some kind of ratio table where they can no longer move their hands. They need to put in the numbers so that the computer will move in that way. And we're very interested in tracking the ways that the strategies, initially moving this way, then moving that way, then figuring out 1 per 2, then noticing the multiplicative relations. We're very much interested to monitor this process and to understand how children are connecting between the different visualizations. So I have this paper where we speak about how children connect and coordinate these visualizations. So here's an example of a child, and the grid has come up, and she was marked by teachers as low performing. But listen, she hasn't even written one symbol on paper, but she's making very interesting connections between the different visualizations. So what else can you say about those numbers, 1 and 2?
1 and 2, then 2 and 4, 3 and 6. Hey, wait. Oh, it's all doubles. The bottom number, like times 2, is the top number. We had like 1 and 2, then 3 and 6, then 4 and 8, and 5 and 10.
Interesting. Huh. So you've said...
Because they're each because this one's always going up by 2, and this one's going up by 1, which would mean that.
Which would mean that what?
That this one is always double this.
Interesting. Okay. This kind of method, it's called a task-based, semi-structured clinical interview, where we try out our new artifacts with the child. We have a protocol that we go through. This is from Piaget, right? And every point where we need to know more, we ask further probing questions. This is Dragan Trninic, who's now a postdoc in Zurich at ETH. So you see this child make connections between different visualizations and actually figuring out that the reason that one is always double the other is because for every one this goes up too, which is an idea that to prove more formally you would need algebra. Yet she doesn't need that because she's understanding at the pre-symbolic level. At this point, I want to make a little shift in the talk now. It's important for me that you understand the contributions of design-based research in that, as I said earlier, when we see something interesting, and we're just like the kids, when we see something interesting in our data, we start digging in. And we think our premise is the better we understand the struggles that students have connecting between naive and scientific ways of looking at phenomena, the better we can hone our own design problems. So it's very curious, and students who come into my course are always perplexed, especially if they've come from the natural sciences. What do you mean we don't have research questions? I say, we don't. We're designers, but we're design-based researchers. I tell them, build the best darn activity you can, and don't worry, the questions will emerge when you're doing data analysis. And it always turns out that what you find interesting as an analyst is exactly where you should be looking in order to understand better how to help children connect these two things. And what I want to do now is to come back to this idea of this gap between the hands. And it's always fascinating in maybe social sciences and certainly in educational research. It's those simple things, but deceptively simple, deceivingly simple things where we need to problematize and think in new ways. Why is it that when children are moving their hands, at some point they're no longer looking at this hand and that hand, but they're looking at the gap between their hands? What is the gap? And I promised you earlier I would speak about concrete and abstract. This gap between my hands, is it here or is it not? Is it concrete? No, it's not. So, like magicians say, there's nothing here, no strings. And yet we can all speak about its properties. It's getting larger and smaller, higher and lower, and we can coordinate between transformations along the two parameters of size and height. The higher it goes, the bigger it is. And yet at no moment are you saying, this Dor standing here, this Dor is crazy, he's talking about something that isn't here. Because it's a real thing for us. Is it abstract? No, I don't think so. It's concrete. It's a thing. We're talking about the thing. So that's why this is for us a laboratory, as simple and rudimentary as this is, to think about how children construct new objects, new psychological objects. We call this thing, we call it an attentional anchor. It turns out from the sports sciences that athletes operate much better when instead of looking and thinking about what they're doing with each hand, they think about moving the one object together. And that's what's happening here. Instead of moving this hand and that hand, now we are moving an object. And it's not natural just to move your two hands flailing around. We're always moving things. The moment you have an object, a thing to think about, some kind of anchor for your attention, you only have one thing to move. You can try doing this. Look at the thing between your hands and say, it needs to get bigger as my hands go up. It needs to get smaller as my hands go down. Okay? Don't be shy. Try it. Come on. So, and remember, you're looking at the thing between your hands. You're making it bigger. You're making it smaller. It's a new thing. It's an object for you, even though a moment ago it wasn't there. And if you think about the two hands, instead this hand needs to move double as fast as this, it's much more difficult. Or this hand has to be always double as high. So in design-based research, we come up with these new ideas. Colleagues have called it ontological innovations, new things, new constructs. And for us, attentional anchor has been really important. So much so that I want to do a little activity with you folks here so you understand better what I mean by an attentional anchor. So this is where you need to not be shy, okay? So we're going to speak, this is going to be group one on this side, and you're going to be the other group. And I'm going to ask you to do something that, just like with the hands, you'll find it's easy to do each one of them, but when I ask you to put them together, it will be difficult. At that point, I will introduce a new structure, which initially will seem really bizarre, but that will enable us to bring the two things together. And I'm doing all of this so that you'll have an awesome moment here at the Very good. And so that I have more ways of speaking about this construct of an attentional anchor. So this is how it's going to work. You folks, how should I do it? On this side, I'm going to ask you to find something that you can slap your hand on. If you have a desk or a knee or on the sofa, okay? And this, okay, so this is how I'm going to do it. I'm going to clap my hands this way. And I'm going to ask you to, with your left hand only, to knock at double speed. So it's tuck, 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 tuck. Don't rush. 1, 2. Raz, dva. Right? 1, 2. Echat, shtaim. Ein, zwei. Uno, duo. Okay, got it. Now let's try this side. You guys need to do with your, stop, thank you. With your right hand, I'm asking you to do this kind of thing. Snap your fingers, but it will be at not a double like them, but triple. So I'm going to do it the same thing, but you're going to go and 1, 2, 3. 1, 2, 3. Don't rush. 2, 3. Good. Okay, stop. Thank you. So I'm going to do this, and I'm going to ask, you guys are going to do your 2. 1, 2, 1, 2. And you can do 1, 2, 3. 1, 2, 3. Okay. Now, those who are doing 2, add the 3. Those who are doing 3, add the 2. All right? Those who are doing 2 with their stamping, add the 3 with their right hand. Those who are clicking with their right hand, add the 2 with their left hand. And stop, stop, stop. Ah! Okay, so you see, you can do each one, but bring them together is difficult. I'm going to introduce for us an attentional anchor. Brace yourself. This is going to be one of the weirdest moments in any talk you've ever attended. So, anybody recognize his face? Oh. This is Janusz Korczak, a World War II hero and one of my favorite authors, a teacher, leader, and children's book author. And so why am I bringing him here? Like, how is he going to help us? It's not because he wrote books or worked with children. It's because of something else. It's because of his name. And in particular, we're going to do a little karaoke kind of experiment here. So I want you to say with me the following his name this way. Janusz Korczak. Janusz Korczak. Say with me. Janusz Korczak. Janusz Korczak. Janusz Korczak. Yeah, okay, very good. Now, what are we're going to do with this? We're going to use this structure in order to figure out how to do the 2 against 3, all right? And this is how we're going to do it. When I say ja, for Janusz, ja, you're going to do both of them, okay? So ja, then nush, Korczak. Again, Janusz Korczak. Janusz Korczak. Janusz Korczak. Janusz Korczak. Look at you guys. See? You can write in your evaluation form that you learned something today. All right, now why does this work? It works because I've taken 2 and 3 and I've separated the name this way onto 6 beats, okay? That's why it worked. So how are we going to do 3 against 4? How would we do 3 against 4? 12. You want 12, okay. So who's going to give us 12? Structure of 12. Another favorite Polish hero of mine. People recognize it, huh? Okay. Not that I can pronounce a name. Wisława Szymborska? Okay. So it's going to be like this. Wisława Szymborska. Wisława Szymborska. Wisława Szymborska. Wisława Szymborska. Wisława Szymborska. Okay. So Wisława Szymborska. Wisława Szymborska. Wisława Szymborska. Look at you guys doing 3 against 4. Amazing. You're having an awesome moment at the Copernicus Science Center. The crazy professor from Berkeley. Yeah. Okay, so, okay, I think you get it. So, again, it's 12. So, that was easy, but why? All right? So, you had a challenging task. I gave you 2 simultaneous and independent motor action patterns. And you were receiving online sensory feedback to evaluate performance initially. But despite understanding the goal, we all face a sensory motor overload, like, how do I do that? So we need somehow to relate across the 2 actions so as to coordinate them. And so we need some kind of frame of reference, a structure, unit, or form. So I introduced for you a supplementary form. It was an articulated goal structure. Right? The goal structure was like an object. It's a thing that I put that constrained the way you were acting. It was something like in the world. And you yourself were generating and maintaining that structure. Went 1, 2, or. And you were attending to that structure, and the structure collapsed 2 jobs into 1, because the hands were doing that rhythm. So the challenging task became a single co-anchored bimanual, 2 hands, bimanual coordination. The structure that I gave you served you as an artifact. It's a tool that mediated the enactment. It was as if it was standing between you and the world, enabling you to do that. And the successful enactment was magical, but then with time it became normal as your attention could shift. You were talking, you were laughing. It just became a thing that kind of became automatic. You could attend to other aspects. And this structure, it also mediated concerting, meaning we were all doing it together, which is not trivial at all. And it's easy to teach and learn and mark and document and remember. And in fact, once it was represented in that structure with the numbers, in some kind of visual form, it can even ground some new content. So I say, oh, 3, like if we wanted, I don't know, 7 against 5, right? So we'll have like 35. We won't try that. And yeah. So I call this thing an attentional anchor, right? Now, I'm aware of the time, and I know that I need to soon. So what I want to do is to rush forward and show you some work we've been doing with tracking children's eyes, okay? So here's stuff that I won't talk about today. We built this, the same thing, the mathematical imagery trainer for proportion for iPads. We worked in schools. I have all these cool videos. At some point of doing this work, we received some. Remember that guy? I liked him. Yeah. And then we built an artificially intelligent teacher that's living in our lab. So I'm just rushing forward. I just want you to see a picture of this.
Our virtual teacher has a name. Meet Maria.
So Maria lives in our lab, and she teaches children to move in new ways, and she interacts with children, and she can feel where they're pressing.
Let's try something else. Start at the bottom of the screen. You can only move 1 hand at a time. Start with your left hand, move up just 1 square. Then move your right hand to make the screen green. Nice!
Yeah. So there are many directions and we're just generating more questions. And meanwhile in Utrecht, my collaborators were doing eye tracking work. Eye tracking work is really fascinating because you can see not only where what the children are doing with their hands, but you can also see where their eyes are, where they are looking. That's that orange stuff over there, okay? So, for example, here you can see the child is working with this mathematical imagery trainer, and you can see the eyes are going to the left, going to the right, and then at some point, suddenly the child will look halfway up the bar, and you'll see that there's a new kind of pattern of motion of the eyes, all right? So we're looking to understand this attentional anchor. See that? Start to look halfway. And there's no visual stimulus there. There's no thing to look at as such, but they're looking at that nevertheless. So we found all these typical eye tracking patterns and, well, published, because that's kind of what we do. And I want to finish off by speaking about this eye tracking study where we were working with orthogonal. So this time, instead of moving their hands this way up and down, we gave them a task where we collapsed this axis down, okay? So it's not this way, it's now this way, okay? Well, for you, it's like that, okay? So the children need to move their hands and keep the screen green. And here's what the eye tracking has enabled us to see. Because if initially the children, they're moving their hands and you see the eyes are going to where the fingers are, at some point we started noticing the kids are looking in the middle of the screen where there's nothing. There's nothing there to see. And yet they look there.
Ja, die had je net al. Maar je kan ook allebei je vingers bewegen, of zeg?
Some Dutch speakers, yeah? So we asked the kid, like, what are you doing? How are you doing this?
Is dan deze ook verder weg, die rechter, dan die linker?
Ja, wel iets, maar het blijft wel zeg maar op één lijn zo.
Blijft wel op één lijn. Ja. Okay.
It's important for me to emphasize here that the experimenter does not have real-time, at least in this experiment, did not have real-time access to the eye tracking data. And this kid is saying, I'm looking at the line, and she's like, yeah, okay, but she didn't know what he means. Turns out what this child is doing, and more children later we saw, in order to move their hands this way, they started imagining a diagonal line that's connecting their fingers. So if you look at my two fingers, imagine the diagonal line that's connecting them. What I'm doing now is I'm not moving my fingers as such anymore. I'm moving this line across, keeping it at the same angle all the time. And that's all I need to do. When I do that, the whole thing becomes easy. I have a new attentional anchor. So the eye tracking data enabled us to figure out how the kids are doing it. So much so that in the next round, when the teachers already knew about this trick that kids are doing, they could literally speak to them.
Een lijn zou voorstellen die van je ene vinger naar je andere vinger.
Ja.
Speak to them about this imaginary object. So now the teacher and child can imagine this object together. And it is through the eye tracking work that we could come to discover it. So they speak about properties of an invisible object. Is it abstract? I don't think so. And here's the last slide. Just a shape of things to come. We are now working with dual eye tracking, where the teacher and the kid both have their eyes tracked. And never mind what this actual task is, but the red is the teacher, the yellow is the child. And you can see, we can track to see if they're together or not. So here the teacher and child are looking at different places. But for instance here, you can see how the teacher is very closely following the child. So this is opening for us a whole new kind of horizon of work that we're currently doing. This one is with collaborators in Moscow. So this idea of the attentional anchor we've published about. My objective here was to show you how in design-based research we're both creating products that we can validate and develop and take into schools and scale up, but at the same time through that work we're honing more and more what specifically are the challenges children are facing in connecting between their intuitive ways of seeing the world and the cultural ways. For example, the eye tracking revealed to us that the kid was seeing an invisible diagonal line, but then we brought on a grid that was this way, and the kid was having trouble connecting them. So now we know better, the next round, how to steer the children to look in particular ways or how to give them the resources that they need in order to better connect between the naive and scientific ways of looking at the world. So with Child's Pose, I'll say thank you. So I believe we still have some time for questions. Is that true? Yes, so I welcome your questions.
Okay, so is there any particular age when kids know that there is a proportion? When they are 4 or when they are 6? When do you know?
That's a fascinating question. I mean, to figure that out, we would have to do what's called cross-sectional studies of trying the same experiment on 3-year-olds, 4, 5, 6, 7, etc. We have not gone in that route, but I'd be very welcoming anybody who would want to try that. For sure, it is much easier at any age to move your hands, keeping the same distance between them, to move otherwise. And we have gone as young as 7. We've seen that. It just so happens we haven't. See, the difference is that we are not, I guess, like educational psychologists or cognitive developmental psychologists. So my colleagues would do that. For instance, the work of the baby, remember, who at the age of half a year could make those the discernments of distribution. That's my colleague across the hall. Her name is Fei Xu, spelled X-U. And she's the one who works with very young children, and she wants to know at what age people can do what. Because we are design-based researchers and a bit closer to schools, we find we're inclined to try and work with the kids more or less of the age when they would study that in school, usually just before to make sure they haven't studied that, because then we can bring our resources to teachers. So I'm as curious as you to know at what age that happens. And also, maybe I'll just mark also that I try to be careful with my wording. So I would not necessarily call that they understand proportion, rather that they can learn to move in a new way, that they begin to signify mathematically and discover also the symbolic notations that go along with that. And thanks for the question. Marcia.
So how do you do transfer? So you're actually dealing with transfer in your paradigm mapping, trying to make it more abstract. But how do you view transfer? What is necessary to get transfer?
Okay. So in a study that was conducted by Carmen Patrick, now Carmen Patrick Smith, professor at the University of Vermont, she did her entire dissertation on this paradigm, and she worked with 7 middle school classrooms, and she found conceptual gains for children who worked with our system as compared to other ones who did compatible activities. And so she asked them questions like paper and pencil questions about proportionality. The way we are taking it is we have the kids work within the interactive iPad, and then we shift to work with paper and pen, and we ask them to show us what they were doing. And through the conversation, we start highlighting properties. For example, speaking about the kids who were, some kids looked at the diagonal, other kids were saying, I'm looking up here, and I want the rectangle to always grow. So they're looking at a point there. So then they draw the rectangles for us, and then we start measuring them and start noticing the numerical properties. Or with the triangles, we're thinking of taking that into trigonometry as well, because it's the same angle, and so the trigonometric functions are constant. So we look to see the progressional sequence as one that goes from the action through to the representation, and finding out through measurement to find out properties, and so to create a discourse around that. And yeah, a goal would be down the line to take it even further to other situations. Yeah. Back there, sir? You. Yes.
So for me, learning is always a social endeavor, right? And I also see you have a kid, and then you have this old two dudes talking to the kid, and then later on you have the avatar. For me, it's important that it's social, because in talking, I actually start to formalize my theories. So would you also observe this, that kids would start formalizing their theories when they work with the avatar?
Oh, I thought you were going to ask about kids working in pairs. For some reason, I've lost that image here. With the avatar, it's really an interesting process, because on the one hand, the idea is to bring to scale our work. Because it's one thing with me or you or one person working with a child or even 2 children, but what about millions of children everywhere? So the idea is, as the artificial intelligence becomes more sophisticated, more children everywhere can have these experiences. So research is showing that children, especially young children, form some kind of social relationship with this cognitive, virtual pedagogical tutor. And as the years go along, these things will become like science fiction, right? So the questions are not necessarily about how things are now, but more about where things will be in 5 or 10 or 20 years. I can imagine that these avatars will become more and more intelligent and therefore more sociable. Personally, I don't want to see avatars replacing humans, but to the extent that we're embedding more and more guidance into these implements, though they might as well use as much of the modalities as possible. Because it's one thing to interact with just text, and another one to interact with this avatar who's showing you and pointing and responding to the way that you're working. Okay? But another way of going around that is having kids work in pairs. And I know I'm out of time, but I have a slide I can show you later of children doing this work in pairs, where one is holding the one, the other is holding the other, and you see how they have to coordinate a joint activity of moving it and keeping it green. So just because they need to coordinate the joint activity, they start speaking in language that becomes increasingly mathematical, because they need to solve the pragmatic problem of joint activity. So they're generating language. It's a very Wittgensteinian idea, the page 1 of Philosophical Investigations. The word, the speech, the language sprouts from the need to coordinate.
Okay, thank you for your talk, because it was very inspiring, and I hope to put in practice some of your ideas. I think in your model, the learning model, the body is very important. And I ask you, how do you deal with the children who have some kind of impairment? They can't move properly, they can't hear, they can't see, or whatever.
That's an absolutely fascinating question. Our lab is very much concerned with access and with children with special needs. In fact, right now I'm authoring a paper about ideating new design for blind children. And what is fascinating about this work, it's called UDL, Universal Design for Learning. What's fascinating about it is that the solutions that we create for children with special needs almost always permeate into classrooms for typical, sensorily typical children also to enjoy. So for example, in the iPad version, we have what's called sonification. So instead of just seeing colors, you can hear sounds. So you're trying to move your fingers, keeping it silent. If you go off, you go, you try to make it sound as you move. So when I have a blind colleague who's helping me develop that. I learned a lot from him, because the moment he grabbed this, he put his thumbs at the bottom. And I said to him, Josh, why are you putting your thumbs at the bottom? And he said, well, duh, if I adjust my fingers, I don't know where they are. Okay? So so from that we learned that we need to put little hinges here, for, like little rest for the thumbs. So it's through that work with those students that we learn. You could ask a deeper question. What about children who have motoric problems, who could never move? What does that even mean for mathematics? And I think that's a question for developmental psychologists studying physiology and motility, motion, because, and how it relates to cognitive development, at least from the work that I know on animals, on mammals, on cats. There's classic work that shows that people who cannot necessarily move their hands, then they cannot exercise agency in interacting with the world. Even if you show the world onto them, they don't develop sensory motor schemes. However, these days there are kind of workarounds where there are brain-computer interfaces which enabling people who are paraplegic even to move objects around on a screen. So I don't know what the state of the art of that work is, but to the extent that you can use your agency in order to interact with the world and transform your own ecology, you will develop the sensory motor schemes, that they're kind of phantom motor, because the brain is there and it's plastic. So it experiences the motion as if there's an arm that's changing. So you will develop the sensory motor schemes that presumably could undergird the mathematical concepts. Sir? So again, these words are concrete and abstract are really curious. Some of my colleagues say to me that those words don't do work for them. It doesn't give them traction. But I want to tell you about expert abacus users. These are folks who learn to do basic arithmetic with an abacus or soroban. It turns out that they can do in rapid speed calculations of multiple digits times multiple digits And they practice so much that at some point, they no longer need the object itself. You can see videos, I can show you videos of kids. You give them like multi-digit times multi-digit, and they sit there, you can see them gesturing with their fingers, and they write out the answer. So I ask you, is that abstract or concrete? You see? Because these are sensory motor schemes that have brought them to the point where they can actually distribute their thinking onto an imagined object. So much so that people who studied Stigler and Hatano and Miyake, who studied expert abacus users, they gave them a dual task, like a masking task. They told them, yeah, here's a ball, squeeze the ball while doing this calculation. Well, the novices couldn't do it at all. The advanced or the masters could do it, but much slower. But the few, like 3 top masters in Japan, were not disturbed at all, meaning the connections were so strong that they could do these gestures with these balls. It was no longer taking cognitive resources in a way that was impeding that work. So my point here is, at what point along that developmental continuity of skill would you say that it stopped being concrete and became abstract? That's what I mean. These words just don't work for me anymore. Okay? And just like that mathematician who said he has all these imagery and he rolls on the floor. What is that, right? Sir?
I have the general question about, because you present some examples of learning some kind of concept on very elementary level. But I just wonder whether it's possible to obtain some better understanding when learning more abstract mathematical things like functions. For example, logarithms is very problematic for the pupils, and some exponential function by just moving them. Moving and then trying to understand what happened with the formulas. Yeah. In this sense, moving could be more general tool, maybe, for understanding even very abstract mathematical concepts.
Absolutely. So once again, this word abstract, it's from my perspective, from enactivism and phenomenology, this word abstract just doesn't mean for me the things that, of course, colloquially I can use it, but through analysis, not. In 1945, a book came out by Jacques Hadamard, and he had interviewed the most famous, preeminent scientists and mathematicians of the time, including Henri Poincaré and Albert Einstein and others. And across the board, these people saying to him, yes, what does it mean for you to think? And only a fraction of them said that they think by writing these notations. Most of them, including Poincaré and Einstein, said, it's these images, it's these clouds that are moving, and I'm trying to organize these things. And for certain, when I've interviewed topologists, people working on topology, they're gesturing like mad. And when mathematicians are speaking to each other, they're moving their hands all the time. So, but it all comes down to this, I'm admittedly and deliberately very rudimentary, very simple thing that I'm telling you about. This thing that isn't here, is it abstract or is it concrete? It's a new thing that I can think about. It's a new information invariant. So I'm moving in a way that I'm keeping invariant this structure. It's a new structure. It's a sensory structure that is guiding my actions. It's a new sensory motor scheme. So mathematical learning is the development of new sensory motor schemes that you can also represent within the semiotic register of symbolic notation. So when we see a person writing, it's not the case that it's all just about creating those symbols. Rather, that is just the tip of the iceberg of the embodied sensory motor reasoning that is going on. And as the paradigm shifts in cognitive science and people are beginning increasingly to appreciate alternative paradigms of what it means to reason, we will see more and more work that is bringing forward evidence to support the claims that mathematical reasoning too is inherently sensory motor.
I am Lech Nowicki from Copernicus Science Center. I would like to answer the question which was posed just a moment ago in such a way that here in this building, in our exhibition, we have an exhibit titled, "Are You a Function?" It is an exhibit in which we move along a carpet, and we try to follow a line on the screen. It is just about function, about diagram of a function. So in this way, we try to do slightly similar thing, like, let's say, proportionality. Of course, it's hard to imagine that we can show everything in mathematics in such a way. It's probably impossible. However, even such notion like function, we can try to manipulate, yes, to use manipulation or body movement to show. Mm-hmm. In fact, to show by mind, yes, by action.
Yeah, thank you for that. I look forward to seeing that exhibit. In fact, a senior colleague of mine at Berkeley, Andy DeSessa, the other day he stopped me in the hall. He said, "I had a Dor moment." I said, "What is a Dor moment?" He says, "I was speaking to my students about calculus, and suddenly they said, 'Look, Andy, what are you doing with your hands?' I said, 'What?' He said, 'I didn't even notice. I was speaking about delta and epsilon, and I was doing this.' My students had to point it out for me. I didn't even know that I'm saying I'm doing this thing." Okay.
Maybe the last question, I think, but I was just thinking about your presentation here and being totally out of field. This may seem a bit odd. I normally work in oncology. But you mentioned yourself that a mathematician who invents his own ideas to experience abstract things, you know, like rolling over on the floor. And I was just wondering if you ever tried to work with more advanced people to help them understand things you may not understand yourself?
I began my talk by speaking about notions of probability that I had thought I understood. It was through building tools for children to learn that I understood it in a deeper way. Because you cannot escape. When you are a teacher, you cannot escape deep understanding. So even though, you know, I'm ashamed to say I passed the tests as a teenager, I had to come into my 30s and 40s to realize that I didn't really understand in any deep way. So in some sense, I'm angry at my own school that they let me pass because I never actually understood. So in a sense, I was teaching myself new ideas through trying to concretize and embody them. And that is how I think Janusz Salk, who found the cure for polio, he describes how when he thinks, he tries to imagine he himself is the virus, right? Barbara McClintock, the Nobel laureate at Yale, she used to think, what is it like to be corn in the field, to understand the genes? And these ideas were brought forward by people like Seymour Papert, who spoke about sort of first-person reasoning and agent-based modeling. It's just like before I said to you, okay, move your right hand. I needed sort of to turn to figure out if it was your left or your right hand. I need to bring things into my own body in order to understand them. So it starts from a what's called egocentric experience that I simulate, and then I go into the allocentric place where I can have the bird's eye view and I can create the representations. So it turns out, to answer your question, that the most advanced scientists in all the fields think in that way by being the sheep, being the wolf, being the corn, being the virus.